In this video, we're going to look at how energy and momentum is carried by electromagnetic waves. And this is in chapter 34.6 and 34.7 of the textbook. Okay, so first off, energy and electromagnetic waves, right? So, well, they're electromagnetic waves, they're electric and magnetic fields, and we've already seen that there's actually energy stored in electric and magnetic fields. So a common thing you can do is define something called the Poynting vector. And the Poynting vector, well, it's a vector, not surprisingly, and it's the power flux. So it's the energy, remember power is energy per time, and flux is per area. So it's the vector, energy transported per time per area. So in the Poynting vector, typically you use a capital S, it is a vector, and this energy flux or power flux, I should say, is actually proportional to E cross B. So it's the cross product of the electric and magnetic fields, and you need a 1 over mu naught constant out in front to make the units work out. So the units, well, it's power per area. So power is in watts, area is in square meters if we're in SI units. And if remember the last video, we talked about the wave equations, right? So that was the sine kx minus omega t. So you can actually, if you actually plug those in for the electric and magnetic fields, so then you can work out what the Poynting vector is. So when it actually changes with position and time, so it's a function of x and t, and you're going to, well, it's the same 1 over mu naught constant. So there's the maximum electric field times the maximum magnetic field times sine squared of kx minus omega t. And we're looking at waves traveling in the positive x direction, or the I hat direction. So the direction of the Poynting vector is the direction of the velocity of the wave, since that's the direction that the energy is flowing. So we've got an I hat here. Now, intensity you can also define, and intensity, since the Poynting vector is changing with time, you can actually average that out over time and define something called intensity. And the intensity, well, it's basically, since we have a sine squared term in here, the average of sine squared is a half, so that's where this 2 comes from. So the intensity is 1 over 2 mu naught E max times B max, or you can also remember, we also saw that the electric field and the magnetic field were related to each other by this factor of the speed of light c, so you could write this in terms of only the electric field or only the magnetic field. And if you have a point source, so let's say you have some point source of electromagnetic waves and then it spreads out in all directions, then the intensity is, well, it's the average power emitted by the source divided by, and it's sort of spreading out in a sphere. So, and the surface area of a sphere is 4 pi r squared. So that's where this term comes from. Now, so electromagnetic waves carry energy. Interestingly, they also carry momentum. So, or another way to think of this, so let's see, so an electromagnetic wave will exert a force on a charged particle that it encounters, changing its momentum, right? And if we want momentum to be conserved, then electromagnetic waves must also carry momentum. So if we have a charged particle, right, so, and it's hit by an electromagnetic wave, right, so the momentum transferred, right, so little p here is the momentum now, it's the energy divided by the speed of light, and or q over c, where this capital Q is standing for energy now, and it doesn't have anything to do with electric charge anymore. And this is if your wave is absorbed by the charged particle. Now, in principle, right, so you could also have a wave comes in and then reflects back, and for a perfect reflection, well, and this is, if you remember back when we did momentum conservation, so you get this factor of 2, right, because the change in momentum is doubled if it reflects off. So it's 2 times the energy transferred over c, or 2q over c. So we can also define pressure, right, since we decided that electromagnetic waves are going to exert a force. Well, if there's a force, there's also going to be a pressure, right? Pressure is just force divided by area. So if you have an absorbed wave, then the pressure, capital P, is force per area, which is actually the intensity of the wave divided by the speed of light. Or if you reflecting the waves, remember we get this extra factor of 2, so it's 2 times the intensity of the wave divided by the speed of light. And there's actually a nifty application to this, something called solar sails. So if you're building, say, some sort of a space probe or something you want to send off to, the farthest reaches of the solar system, in general, propulsion is hard because you have to carry your fuel with you. So people are actually working on these solar sails. So it's this basically a big reflective surface. This is kind of like a tin foil, although it's actually much, much lighter than that. And it's a large area, and it's actually sunlight. So light is an electromagnetic wave. The sunlight will bounce off this solar sail, and that'll actually give a little bit of momentum to what it's attached to. So it's one way to actually, well, it's a proposal to actually propel space satellites to very, very large distances.